We've mentioned that exchangeable random variables are identically distributed, but identically distributed random variables aren't necessarily exchangeable. Now let's look at independent and identically distributed random variables and see how these random variables relate to exchangeability. So let's look at the discrete case first. So discrete random variables, x1 through xn, with probability mass functions, let's say p1 through pn, are independent if the probability that capital X1 equals little x1, etc., through capital Xn being little xn equals just the product of these probabilities, which we could write as the product of the probability mass functions p1 of x1 up to pn of xn. Now x1 through xn are identically distributed but not necessarily identical. If there is one probability mass function, let's say p, such that the probability that xi equals c is just little p of c for I equals 1 to n, and for all values c. So combining these properties, x1 through xn are independent and identically distributed. Well, this combination of properties comes up often, so sometimes we write IID, independent and identically distributed. If the probability that x1 equals little x1 through xn being equal to little xn is just p1 of x1, p of x1 through p of xn. So we don't need any subscripts because all of these variables have the same probability mass function. Alright, let's look at the continuous case. So continuous random variables I'm going to write down joint probability density functions and cumulative density functions and individual ones. So with joint probability density function, let's say capital G, no, that would be a joint cumulative distribution function if I'm using the capital letter, and joint probability density function little g And marginal cumulative distribution functions, I'll use f for these, f1 of x1 through fn of xn. This should be capital if I'm saying cumulative distribution function. And marginal probability density functions, little f1 of x1 through little fn of xn. So these are independent if the joint cumulative distribution function factors as a product of the marginals, or equivalently if the joint probability density function factors as a product of the marginals. And these variables are identically distributed if there is one cumulative density function, capital F, or equivalently one probability density function, little f, such that the probability that xi is less than or equal to c is f, just capital F of c, for I equals 1 to n, and for all c, and this is the integral as t goes from negative infinity to c of little f of t dt. So then x1 through xn are independent and identically distributed if the joint cumulative density function gx1 through xn factors as f of x1 through f of xn, and the joint probability density function g of x1 through xn factors as little f of x1 through little f of xn, where we have no subscripts needed because this capital F works for all the random variables, this little f works for all the random variables. Alright, now identically distributed random variables aren't always exchangeable random variables, but it turns out that independent and identically independent and identically distributed random variables are always exchangeable. So if random variables x1 through xn are independent and identically distributed, then they are exchangeable. So to prove this, let's look at the discrete case first. The probability that x1, let's let let's fix n values a1 through an. And let's let b1 through bn be a rearrangement of a1 through an. Then we have the probability that x1 equals a1, etc., and xn being equal to an equals p of a1 through p of an, where p is the probability mass function of any one of those random variables. Now we also have the probability that x1 equals b1, x2 equals b2, etc., up to xn being equal to bn is p of b1 through p of bn. But since b1 through bn is just a rearrangement of the numbers a1 through an, these products are equal. Because when we take real numbers and multiply them, we can multiply them in any order and get the same product. And if we look at the continuous case, the probability that x1 is less than or equal to a1 through xn being less than or equal to an, is f of a1 through an. Sorry, I'm going to write f of a1 through f of an, where capital F is the cumulative distribution function of xi for all I. And the probability that x1 is less than or equal to b1, etc., and xn is less than or equal to bn is just f of b1 through f of bn. And again, since b1 through bn are just rearrangements is just a rearrangement of the numbers a1 through an, then we're multiplying the same numbers here in a different order, but multiplying in a different order doesn't change the product. Alright, now let's look at some simple experiments and analyze them for independence, identical distribution, and exchangeability. So let's say an urn contains 4 blue and 6 white marbles. And let's assume we have inspected it well. Let's choose 3 marbles with replacement. Let's let xi be the color of the ith marble chosen. So first thing I want to claim is that x1, x2, and x3 are independent and identically distributed. The reason is, assuming that we've inspected the urn well, our opinion won't change. With observation. So the probability of the ith choice being blue is just the probability of the first choice being blue, which is 4/10. And the probability of xi being blue given x1 being blue is just the probability of xi being blue. This earlier observation doesn't change our opinion at all. Or maybe more to the point, I can write probability that xi equals blue given, well, there's only 3 observations here. Even if xi if I were 3 and x1 were blue and x2 were blue, that would not influence our opinion of x3 being blue. So observation is not changing our opinion because of our thorough inspection ahead of time. Now I claim that these are exchangeable. Well, they have to be exchangeable since they're IID. But let's just look at that exchangeability. So the probability of, let's say, blue, blue, white is 4/10 times 4/10 times 6/10. The probability of blue, white, blue is 4/10 times 6/10 times 4/10. And the probability of white, blue, blue equals 6/10 times 4/10 times 4/10. So we can see that these are the same 3 probabilities being multiplied, just in different orders. But of course, multiplying real numbers in different orders gives us the same product. Alright, now let's choose 3 marbles without replacement and compare and contrast. And let me use different letters for the random variables. Let's let yi be the color of the ith marble chosen. Alright, first I claim, let's call this claim C because I've made 2 claims already. First I claim that y1 through y3 are not independent. To see this, we'll just compute a couple of conditional probabilities. probability that y2 is blue given that y1 is blue is, so if we're not replacing, y1 is blue, we've taken one blue out of the urn, we have 3 blue left out of 9 marbles left. So 3/9. And the probability that y2 is blue given that y1 is white is, so we have 4 blue marbles left in the urn, but a total of 9 marbles. So apparently observation of y1 does change our opinion about y2. 4/9 and 3/9 are not the same. On the other hand, y1, y2, and y3 are identically distributed. And the reason is, well, we showed this in a previous video. The probability that y1 is blue is 4/10, and that equals the probability that y2 is blue also. So since these are identically distributed but not independent, we can't say that they're independent and identically distributed. So they're not independent. And just to remind you, we showed earlier that y1, y2, and y3 are exchangeable. And the reason from the previous video is that the probability of blue, blue, white, probability of blue, white, blue, and probability of white, blue, blue are all the same. And same things for 2 whites and a blue. So the order of the outcomes doesn't matter. We all get the same, we get the same probabilities for all different orders. So to summarize the relationships that we have between independence, identical distribution, and exchangeability, x1 through xn are independent and identically distributed, then that implies that x1 through xn are exchangeable. And that implies that x1 through xn are identically distributed. So we really have identically distributed in all 3 of these cases. So this, what we can take away from this is that independence is a stronger property than exchangeability. And if we were to draw a Venn diagram of sets of random variables, so in the big picture we could have identically distributed random variables. Then inside of that we have exchangeable random variables. And then inside of that we have independent and identically distributed random variables. So this is the most special class out of the three. Then exchangeable is the next most special, and then identical is a bigger class than that. The end.